Hello, good afternoon. My name is Kanishka Ravin Ratnajoti, and this is my demonstration for my final year project. My topic is enhancing personalized contextual and temporal recommendations using multitask learning. And I will be using the movie lens dataset, so hence the movie lens case study. Uh, so this will basically be a demo application on how the movies will be recommended based on this new framework. This can also be used for different domains after by configuring the framework in regards to the data sets to be trained. So let's move on. Traditional recommendation systems face significant challenges in the digital content ecosystem. Current approaches primarily rely on single task learning models like collaborative filtering and context based filtering, which fundamentally fail to capture dynamic nature of the users. So basically, they give static interpretations for user interests and not capture the dynamically evolving behaviors of the user, hence leading to outdated recommendations and limited consideration of contextual factors. And the temporal factor is a new feature entering the recommendation domain, which is based on the times user interacts with the system to recommend items based on the timely factor, basically. Yeah. So let's take a look at the concept map and take an idea of the project scope. And yeah, so this will be the concept map, the domain being recommendation system machine learning, and the limitations currently is static user preference, as I said earlier, and lack of contextual awareness. The cold start problem is a well-known issue that has been there from the beginning of recommendation systems. Many systems handle it very differently by showing new users their top ratings, taking prompting users to select categories that they prefer on entering the application, and the other one is data sparsity, which is something also a very old issue that has been persisting and was hard to combat. Data sparsity meaning how to deal with lack of or incomplete data. So a single user can rate multiple movies, but also there might be some movies which are not rated by any users. So how do we suggest these movies to the users? So this is a part of the data sparsity problem. And as for existing works in algorithm, there's the famous collaborative filtering, context-based filterings. Then there are also a few highly still research level stuff like TARS, more like time-aware recommendation systems, and MKR, like knowledge graphs using. So knowledge graphs, a big downside is the high performance high performance demands. And yeah, and SASREC is also a new implementation called self-attention. And yeah, so mainstream data sets which are readily available for this research domain is the movie lens dataset and also the IMDb dataset. These are the mostly commonly used two datasets in the domain of movie recommendations, which is why I went with movie lens dataset due to its newest release of 32 million record dataset. Then moving on to technologies, a project like this would require a, some sort of framework to build upon. So that's where the TensorFlow framework comes into play. And these are other things that are used in the field of recommendation system, mixture of experts, recurrent neural networks, and Python data libs like surprise lib, which comes with the SVD singular value decomposition methods and everything. These will basically generate they'll have pre-built models which you can train with your dataset and then use it readily in your application, which I used later on to compare with my model, which we'll get in that in a second. And then we have the multi architecture, the applicable areas. This could be applicable in e-commerce, streaming services, movie recommendations, streaming, social media, content platforms. But yeah, we'll be focusing on the movie recommendations for this project. And evaluation. So there are a lot of ways to evaluate a recommendation system. Some of the key features would be RMSE, root mean square error, MAE, precision, recall, diversity. That means a recommendation system should also provide recommendations based on users' preference, but also in a diverse context, as in not just action category because it's just the user has watched an action movie, but also movies similar in other categories as well. So this is what we mean by a diversity score, and also the model benchmarking. So that would be the context diagram. Okay, and then we will take a look at the system architecture of the multitask learning model. Yeah, the key components: the shared feature extraction layer, task-specific branches, the auxiliary tasks, temporal modeling, and contextual integration. Yeah, take a look at that. So this is how the data structure, the data tiers would be, the tiers will be looking like. Yeah, then first we have the data layer, which will have the data sets, the how the data sets will be converted into feature engineering and chunking data for processing. The data will then be fed into the model layer, the shared feature extraction layer, which will help the model train faster by using the same data in all three auxiliary tasks, which is like rating prediction, temporal modeling, and tag prediction. So different algorithms will be used for each of these branches. Like for rating prediction, we'll use collaborative filtering, and temporal modeling will use something called cyclic encoding. This is a new concept. And then for tag prediction, we will use tag weights and scaling, enhanced focal loss. Then the model layer will feed down to the evaluation layer. This will basically be sending the recommendations where we can check the RSME, MAE evaluation scores, diversity, similarity, and also generate recommendations, as in top 10 recommendations for a user based on the user's preferences. And then we finally have the API visualization layer, which is the front end, where we can show this to the user and compare these models. Okay. Moving on, let's look at the technical implementation, the technology stack, model architecture, the code, and the key algorithms, the pre-processing techniques. So, to talk about the tech stack, this is mainly using Python with the surprise lib for other models to generate the model using TensorFlow framework. And so, this would be the code for the model. So we I'm using the movie lens 32 million records data set here, as well as movie lens small data set, which is 100,000. This is used to train the other models and also a version of my model, so we can compare the two. And the process movies and process tags. So these are functions used to, these are pre-processing functions to feed the data into the multitask learning model, and how we'll need to structure it. Yeah. Then the tag weights, and then we can go on. Uh, this is the analyze user movie overlap. There are some movies that overlap. So this is some issues that we felt. We have the process chunks method. This is where, because the movie lens dataset is so big, we had to break it down into chunks and process it after that, as the RAM could not store all the records at the same time after converting it into feature embeddings. So we chunked it into 50,000 records per chunk, and it gets saved here as process chunks, and then we can use them that to feed into the model using a data generator. So this is enhanced focal loss, as we talked earlier, is to improve focal loss implementations optimized for highly imbalanced tag data. So fixing imbalances, these are basically pre-processing steps, and the chunk generator that basically generates and gives batches of chunks with ID mappings. These are the inputs. And for the tag branches, for the tag prediction auxiliary task, we use this method, build and improve tag branch. And yeah, so this, you can see the layers we used, the dense layer, the second dense layer, and the output layer for this branch. And then we'll look into the core of the model, basically the multitask learning model. You can see the inputs we use, the user, movie, and genre inputs, and also the embeddings, user and movie embeddings. Then we have gone through a few flattening layers and genre dense layers. These are all done through hyperparameter tuning and layer matching to get the best results possible for this framework. Yeah, then we'll move on to the compiling part of the model. So each rating, temporal, and tagged outputs are actually weighted. So these are also done through hyperparameter tuning and also some component of research as well, where we looked into which are more important features. Which is the main thing that we're looking to do is rating output, which is the key component of a recommendation system. So that is weighted higher, and the temporal output and tagged outputs, the auxiliary tasks, are a bit lower. And yeah, and then we have the callbacks, the early stopping, where if the epochs keep on decreasing in efficiency of training, the valuation loss, and then we'll stop it. The patience is set for 5 epochs, and then the model checkpoint. If when a model hits a checkpoint an epoch, then it will get saved if it's better than the earlier epoch. And then the reduce LR, this will automatically reset the learning rate of the training after each epoch if it so patience is 2 after each 2 epochs. And it will show how it works. And then yeah, these are some of the parameters of the model. So the batch size is 512, and then we calculate the validation steps for epoch and everything here. Yeah, and this is the trained data set. These are the matrices we'll be keeping track of, and this is the validation data set. The same matrices are kept tracked here as well. And finally, here's the training model part, where we train the model for 15 epochs using the callbacks and the validation data set after to validate it. From here on is basically how to uh, how to model and display the improvement of the model. So this is basically plotting out the epochs against ratings of root mean square error, the tag AUC, and temporal MAE, mean average error. We used a function called predict recommendation. This is to give a few predictions from the model that we just generated to showcase how it works and how it performs. Yeah, so that is the core model. And so this code is used for the other models we compare with the recommendation system. For this, we use the Moviland small dataset, which is 100,000, which we can easily quickly train the few models, including our model here as well, and then output it so that it can work and we can compare them efficiently. So this can also be a way of showing that this can effectively tackle data sparsity by training in smaller data sets as well. Yeah, so these are all these models are based on the surprise library. uh, I call them and then configured them and then generated and trained these models for 10 epochs each. Yeah, here's the training. And yeah. Then here we'll be training the multitask learning model for the same small data set. And then we, yeah, this is the code for that, which will be using the same thing, calculating tag weights, and the same methods used in the above code for the large data set will be used here, minus the breaking down into chunks. As this is just a small data set, we don't need to do the pre-processing of breaking down the embeddings into smaller chunks. We straight away process the data set and feed it to the model. Yeah. Okay. Then I guess we can move into the code part of the front end and the back end. To show you the structure of how the application would look like, this will be a Flask application and with a React front end. So the backend will consist of a few routes, namely the genres, models, movies, ratings, users, and yeah, the database will be built based around these schemas as well. Schemas will be the same. These are the models, and the schemas will be the same. And here are the util functions, which is where the recommendation models are set. So all the models which were generated from the code in the Kaggle notebook will be set here. So this will hold all the models, the baseline, the genre, the KNN model, and then we have the multitask learning small one, the one trained by the 100K records, and then we have the SVD one, and yeah, all the models will be set into this folder. And as for the front end, would be a React application basically of 5 pages. Here we can take a look at the components. So the important component is user selection, which we'll go through in a second. The user selection will lead to the movie search, and which will have two parts to go to. One would be model selection, and the other would be recommendations or model comparison. So yeah, I will show this in the demo. Uh, So I activate the virtual environment for the backend, and we can run the backend by hitting Flask run. And now the backend is up and running at port 5000. Next, we'll do the front end. Uh, yeah, CD front end, and then we can run node npm run dev, which will open it at this port, which we can navigate here, which will lead into this page. This is the initial page. Here you can pick pre-saved users, or you can create a new user here, basically adding an age, a name, a gender, occupation, or these are some of this explicit tags that we provide that the user can include or not. It's an optional. It can be included or it can't be included. It's based on user preference. So basically, if we add here age 17, male, occupation could be artist, and action adventure, we can add a user. So this will get saved to the database and be added to the list of users. We can select another user, or we can select the user that we already created, and we can continue to movie search. On continue, we have the personalized tab, which will generate personalized information, personalized movies for the user. And this will take a while, as this is using the the larger model used the 32 million records, and these are the recommendations based on the user preferences we clicked. And here at trending would be the top rated movies in the database by all users. So this is an option just to show that these are the highest rated movies throughout the entire system. And of course we can search for a movie here. Nothing found. uh, and of course we can search for a movie like that here. Here we can provide explicit ratings and rate a movie, and these will get saved to the backend into the database as a preference of this user. Next, we have two places where we can go. One is compare models, and the other one is AI model analysis. So, AI model analysis is a way the user can check how it compares against the basic collaborative and context based models. So, if we go here, we can get a chart. This is still loading, and once this load, these values will update. Okay. So once the values is updated, we can see here that these are some factors that we checked for the context-based, multitask, and collaborative. And you can see the relevance score, the diversity score, as well as the coverage is high in the multitask learning than content-based and collaborative-based filtering recommendation systems. And yeah, here users can provide which they like most as an explicit input, which will help provide feedback on which model to use for the user in the application. And yeah, so this is the basic comparing of the collaborative and context based models. Then we can go back here. So here the second feature here is the compare models. Yeah, so this is where we introduce five different models, and we can pick one of those, two of those actually, and compare them with each other, and this will rate how they perform and everything. We'll check that out. Here we can check, let's say, our multitask learning model, and then we can check a hybrid recommender. And here we can set the amount of results we want. Let's set it to 5 for now, and we can generate recommendations. So here it will generate recommendations using both the algorithms based on what it thinks the user would like. And then yeah, you can see here these are recommended based on the multitask learning model, and these are recommended based on the hybrid recommendation system from context and collaborative. And like that we can switch between these uh, different models and set it accordingly. Then we can go to view comparison, and we can check the diversity score, the average item rating, and the recommendations, and the best model out of the two for the certain user for this particular instance. This would be the main code demonstration and the application demonstration for my project. Next, we will take a look at the evaluation results. For the five models we trained, here are the RMSE, MAE rating prediction and error rates. As you can see, the multitask learning model is performing as well, if not better, than the collaborative filtering SVD, KNN, and co-clustering models. And yeah, for future work and enhancements, we could improve the accuracy of the model, make it real-time preference adaptations, and include explainable AI as to why these recommendations were done, and distributed training for large-scale deployment, as in for mainstream applications and industrial products. And this concludes my presentation for my final year project. Thank you.